In this last section of the course, we're going to talk about arc length. This idea of a problem is very similar to the area and volume problems that we've talked about before, except this time this is the one-dimensional equivalent to the area, which is 2D, and volume, which is 3D problems from before. So, looking at this, we had our 3D problems, which we just looked at. We're looking at volumes. So maybe we were looking at a cone, and to find the volume of that cone, we looked at slices. And the slice would look like a little cylinder or a little disc. In the 2D problems, which is what the first ones that we looked at area. And a slice here looked like a little rectangle. Now we're going to be looking at a one-dimensional equivalent, which is going to be looking at the length of a curve. And a slice here is going to be a line segment. So in the 3D problems, we looked at the volume of a slice. In the 2D problems, we looked at the area of a slice. And for this, we're going to look at the length of a slice. The goal of this section is to take a curvy line or a function that's going to be difficult to find the length of because it's not just a straight line. We are going to estimate that by looking at a bunch of straight lines that are easy to find the length of. So again, we can estimate the length of a curve This is what arc length is. By adding up the lengths of many small line segments. And if we have more and more line segments, the more line segments, the better the estimate, just as it was for the other problems that we've talked about in this chapter. So we're going to go over what the formula for this is. The problems are relatively easy because you can just plug them into the formula, but understanding what's going on behind it is a little more difficult. So the formula we have here is that the length of a function, or this is the arc length, or length of a curve on an interval a to b, is given by the formula the integral from a to b, 1 plus the derivative of the function squared and square root dx. And let's think about where this comes from. So first of all, we need to think about what is the length of a line segment. So let's look at a line segment here. This segment is going to start at the point x1, y1, and it's go to the point x2, y2, just 2 points in the xy plane. To find the length of that segment, we can look at a triangle here, a right triangle, where the length of the bottom of that triangle is going to be x2 minus x1, and the height of that triangle is going to be y2 minus y1. And if we are looking for the distance here, we'll call that d, or the length. The distance is going to be, using the Pythagorean Theorem, square root of x2 minus x1 squared plus y2 minus y1 squared, which is the distance formula which you may have seen in an Algebra 1 course or a pre-calc course. And this is the length of a line segment between 2 points. We are going to be saying that the difference in the x values, we're going to call that delta x. The difference in the y values, we're going to call delta y. So we're going to think about the length of a line segment is going to be the square root of delta x squared plus delta y squared. So what we're going to be having here is we're going to have some function f of x. And this function, we're going to break up into the interval a to b. We're going to look on the interval a to b, and we're going to break up this interval into a bunch of different x values. We've done this before in the Riemann sum section. We're going to break this up into x0, x1, x2, x3, x4, on and on and on, all the way to get to the end of x sub n. How many different subintervals we have used to correspond to rectangles. Now they're going to correspond to line segments. So if we look at all the corresponding points on this function, if you want to estimate the length of the curve, you can find the length all of these line segments. And to understand where this is going to come from, we're going to look at just one of these line segments. Let's look at this one right here. This is going to be in between the points x sub I and x sub I plus 1. The distance there is going to be delta x, the difference between them. And the corresponding points up here are going to be x sub I f of x sub I and x sub I plus 1 f of x sub I plus 1. But we're not going to call it f of x sub I. Instead, we're going to call it just y sub I and y sub I plus 1. And we're going to say that the difference in those y values is going to be delta y sub I. So the length of the ith line segment there is going to be what I wrote down before, this delta x squared plus delta y sub I squared. And the total length is going to be approximated by adding up all of those distances from 1 to n. We're going to see how this formula is going to translate into our formula we're given before, but this is really the basis of it, is just from the distance formula, we get this thing with delta x and delta y. So to finish this proof, we're going to go to a new page here. We have now that if n goes to infinity, we have more and more line segments. Delta x is going to start looking like dx, an infinitely small change in x. And delta y sub I is going to approach dy, an infinitely small change in y. So we're going to have here that the length is going to be equal to the limit as n goes to infinity of this sum that we came up with before but we know that when the number of rectangles and the number of subintervals goes to infinity, this is actually going to be equal to the integral of, in this case, dx squared plus dy squared. This is going to be from A to B. And we're going to mess with the integrand, what's inside of the integral, to make it look like the formula we had before. So we're going to mess with this square root of dx squared plus dy squared and square root. First thing we're going to do is we're going to factor out a dx squared out of both terms. So this is going to be equal to square root of a dx squared times 1 plus dy squared over dx squared. And that's going to be equal to just a dx on the outside, 1 plus dy dx squared, and that's going to be exactly equal to square root of 1 plus dy dx is the derivative squared, and then we have a dx on the outside. So our integral, our arc length formula, is going to be the integral from a to b square root 1 plus the derivative squared dx. With that, we're going to do a couple examples. And I said that when we have this formula, it really is just kind of plug and chug. It's not much work. We have to do an antiderivative, but it's pretty much the same every time. So let's look at a couple examples here. First one, find the arc length of a function x to the 3/2 on the interval 1 to 3. Well, the first thing we're going to need to do is find the derivative of that function. And we can use the power rule here, 3/2 x to the 1/2. Make sure you're not confusing derivative and antiderivative. We are finding the derivative here. So then our arc length is going to be the integral from 1 to 3, that's from our bound above, square root of 1 plus 3/2 x to the 1/2 squared dx. And now we just have to do some algebra, and then hopefully we'll have something that we can find the antiderivative of. First, we can square the 3/2 x to the 1/2. That's going to give us the 3/2 squared, which is 9/4, and x to the 1/2 squared is x. If we want to solve this integral, we can use a u substitution. U equals 1 plus 9/4 x. That means that the derivative of this is going to be 9/4. Could write this as du equals 9/4 dx. So we could say dx is equal to 4/9 du. Change the bounds as well. We could have when x is equal to 1, that's going to give us that u is equal to 1 plus 9/4 times 1, which is 1 plus 9/4, which is going to be 13/4. And when x equals 3, you have u is equal to 1 plus 9/4 times 3, which is 1 plus 27/4, which will give us 31/4. So total here we have the integral from 13/4 to 31/4, square root of u times 4/9 du, which is going to give us a 4/9. Antiderivative of square root of u is going to be 2/3 u to the 3/2. Evaluated from those bounds, which will give us 8/27, the constant out in front, 31/4 to the 3/2 minus 13/4 to the 3/2. The length of this curve. Let's do one more problem here. Find the arc length of the function square root of 9 minus x squared on -3 to 0. This problem actually can be done in a much different way. It's not the point of this section, but this is the circle of radius 3 centered at the origin. And if we're going from -3 to 0, we are looking at just this section. And the arc length here should be 1/4 of 2 pi r, the circumference of the circle, or 1/2 pi times 3, the radius, or 3 pi over 2. Using the formula, we would have that the arc length is the integral from -3 to 0, square root of 1 plus the derivative squared dx, where the derivative, we have to use the chain rule here, is going to be 1/2 square root 9 minus x squared times -2x. We can plug that in there, and we can solve. One plus, the 2's are going to cancel out here. I'll get that right there. We'll have -x over square root of 9 minus x squared squared. Square everything in the parentheses. It's going to give us an x squared over 9 minus x squared. Change that into one fraction. Will give us a 9 minus x squared plus x squared over 9 minus x squared. And our last step, we're going to be able to do, write this as square root of 9 over 9 minus x squared, or I guess we could write that as 3 over square root of 9 minus x squared. That's all we're going to be able to do for this problem, is just set up an integral. In order to do this integral, we'd have to use another integration technique you can learn in a Calc 2 course called Trig Substitution, but we're not going to be able to do that. There are not a whole lot of problems we can do for arc length that do come out very nicely in terms of calculation. The best one that we did was actually on the previous page, that x to the 3/2 is very nice. And there are many others that we could do, but sometimes that's all we can get to is just a formula of what that arc length would be.